right, if you're watching, I trust you did well on your quiz just now. Students in here did fairly well. A few little things here and there that we wanted to go over, but otherwise, pretty good job there. One thing that was not on the quiz, you may have noticed, was the theorem I introduced yesterday. And that was Theorem 60. And remember Theorem 60, we had a couple of parallel lines drawn, and from a single point, a whole bunch of transversals could be drawn, at least 3, really, to make anything happen, but could have had a lot of them. And we said this, that kind of like when we had our 2 transversals and lots of parallels, those 2 transversals got chopped up into pieces, and corresponding pieces were proportional. Well, here, it's not the transversals necessarily getting chopped up, it's the parallels getting chopped up. And we said that the pieces of the parallels are proportional in equal ratio. So that if I said that this had a length of, let's just say 4 inches, this was, say, a length of 1.5 inches. Let's say this was a length of 7 inches. And let's say this here was a length of, I don't know, looks like 6 inches. I could call this X, I could call this Y. We could set up a series of equal ratios or a proportion. What would that proportion be, Quentin?
4 is 7, 1.5 is 1. And 6 is 6.
Right, and just like before, we could solve the proportion. Remember, you don't want 2 unknowns at the same time. You can't solve that. But we might, for instance, pair these 2 together to get Y. We might pair these 2 together to get X. And using your calculators, go ahead and find the length of side Y. Leave it in fractional format. So don't enter 1.5, put 1.5 into the calculator. And what do we get for the length of segment Y?
You just want us to call it out?
Go ahead and call it out.
2 and 5/8.
It should get 2 and 5/8 inches for, assuming these were inches, we get 2 and 5/8 inches for that length. How many got the 2 and 5/8? Making sure everyone's able to enter in the calculator properly. All right, Jamie, good to go. All right, go ahead and solve for side X. And what do we get for the length of segment X? Somebody else? Call it out.
3 and 3/7.
Okay, 3 and 3/7 inches would have been our length there. So again, almost exactly like what we dealt with corollary 53-2, just the parallels are now chopped up instead of the transversals. Questions on Theorem 60 from what we talked about yesterday? All right, let's take a look then at the homework. Page 208 in your textbooks. Page 208 in your textbooks. Have your homework proof out. We set the picture up at the end of the lesson yesterday where we had a circle which wasn't actually named. I guess we could name it. How many named your circle? You gave it a name, not like Bob or anything like that, but let's see, Ethan, what did you name your circle?
O.
Oh, all right, so you're boring, a man after my own heart. All right, so we've got Ross right here. That's our diameter. And Ross is extended, so I need to shift my S down so I give myself room to extend it, out to some point D. There was a chord drawn through S, or a chord drawn to S called NS, and this, go around the back, and then this chord was also extended in such a way that at some point, I'd be able to drop a perpendicular right down here, and at that point we had M. So M was the exact extension point needed to drop a perpendicular down to the extended diameter. So we've got this perpendicular here, and this is the picture we should have had. As far as our given, curious to see, how did you state your given, Chris?
Circle of diameter RS extended to D, perpendicular at A perpendicular.
I'm writing fast, but hold on a second. Extended to D, all right.
A perpendicular at D meets chord NS.
What is the perpendicular at D?
M.
So MD perpendicular to RD, right? MD is the perpendicular. Such that
it meets chord NS at a point P.
Point P. I missed something. What meets chord RNS at point P? So maybe we didn't quite have the picture correct. So it started off good, right? We've got the circle, we've got the diameter, it's extended out to D.
I understood it. I guess I just didn't write it.
Yeah, I would kind of take the same approach you did with the diameter, right? You said the diameter was extended to D. Let's now talk about the chord, and let's say chord NS extended to M, so that MD is perpendicular to RD. Maybe something like that. So chord NS extended. Now we were showing both extended. RS is extended, NS is extended. RS is extended to D, that's just a random point. NS is extended to M, but it's not just a random point, it's extended to M such that, meaning there's some requirement on how far this M point has to be, such that MD is perpendicular to RD. Something along that line, probably the best way to phrase it. It has a consistent approach of line extended, but it specifies exactly how that line extends out. Again, how many have something pretty similar? How many's like, yeah, maybe not quite as close, but I understand it now, maybe. All right, quizzes, tests, again, I'll be giving you the given. And then what are we trying to prove? This was very clearly spelled out for us. Chris?
RS is to MS as NS is to DS.
All right, RS is to MS as, you said NS is to DS?
Yes.
As NS is to DS.
We were supposed to rewrite it, right? Like prove, and then I wrote to the side of it, triangle RSN.
Well, no, we're supposed to prove that. That's exactly what we're supposed to prove. That's what it said to prove. Now, analytically, we know, class, if we're going to prove some line segments are proportional, we're going to have to first get some triangles similar to each other, right? So we know that's a necessary step, but ultimately we're not done with the proof until we've actually got the proportional segments. So what triangles, Chris, did you know would have to be proven similar before we can get this?
RSN and MSD.
So you want triangle RSN similar to triangle MSD. How many saw the same two triangles? Again, you're looking at the antecedents, you're looking at the consequence. Those three letters up here and the three letters here, give them to you. So RSN, I don't see the triangle RSN though, Genesis. Oh, okay, so after we get our given, for sake of time, I'm just going to put a line there. We'll just refer back to down there if we need to. Hopefully, number 2, you saw you were going to need to draw.
I forgot to put that. That's why I have 8.
All right, okay. So, yeah, the students were asking me before class, how many steps did you have? And I said, I've got 9, and Ethan says, I got 8. And Ethan just realized, oh, that's an important step. What's the reason, Genesis, for draw RN? Right, those points were already predetermined. You're simply joining them. 2 points determine a stutlen. How many realized we needed this statement and reason and had that in the proof? Good. All right, and Ethan, you realized we needed it. You just forgot to actually put it in the proof.
I'll put it in the picture.
Put it in the picture, but not in the proof. Okay. I want similar triangles. And in order to get similar triangles, I need, Kendall, to get some angles equal. Thoughts on some equal angles, maybe, Kendall?
Angle D and angle N.
Angle D and angle N. Now, Kendall, how would we get D and N equal? What are your thoughts?
They're both right angles.
They are? All right. How do you know this is a right angle?
Because of the perpendicular.
Yeah, in the given it says we've got a perpendicular. So let's go ahead and state next, Kendall, that
Angle D is a right angle.
reason.
Definition of perpendicular.
All right, definition of perpendicular lines. So we know we've got a right angle here. And Kendall, you said we've also got a right angle at N. How do you know we've got a right angle at N?
It's an inscribed angle, and an inscribed angle in a semicircle is a right angle.
Okay, so we actually have to state a couple things, don't we? First of all, we have to state that we have a semicircle, and then we can state that angle N is a right angle because it's inscribed in the semicircle. So number 4, we need to state that
R and S is a semicircle.
And how did you know it was a semicircle?
The
Diameter.
cuts a circle into 2 semicircles.
All right, its diameter cuts a circle into 2 semicircles, and now that we know it's a semicircle, we've got an angle inscribed in the semicircle, so number 5.
Angle N is a right angle.
All right, and simply put,
Any inscribed angle in a semicircle is a right angle.
all right, and the whole reason for the right angles obviously was so we could get,
Equal angles. So angle D equals all right angles are equal.
all right, this is kind of the Kendall show here. So Kendall kind of went on a rampage with us there, getting 4 statements for the price of 1. How many had these four statements, though? It didn't necessarily have to be in this order. These two had to be this order. And we had to get this one either before them or after them before we could get the D and N, but you had those statements. Excellent. So there's a couple of equal angles. Is that enough? Like just say angle, the triangles are similar, class? No, because it's only one pair of angles, right? I got to get some more angles equal here. Ethan?
I numbered the vertical angles at S, and I said they were equal.
All right, so you called these maybe 1 and 2, and you said?
Angle 1 was angle 2.
And of course, we know they're equal because
All vertical angles are vertical angles.
all who vertical angles what?
Vertical angles
Are equal. There we go. All right, and well, in that case, I've got angles here, I've got angles here, so Chris,
Yeah, similar triangles.
by angle, so what should we write down?
Triangle RSN is similar to triangle MSD.
Now, before we go further, well, let's go and get the reason real quick. It's angle. And let's make sure we've got the lettering correct. R is the angle we don't know anything about. So it's got to be equal to the other angle we know nothing about, which would be angle M. Okay, that checks out. Then the angle at S and the other vertical angle at S have to match up. They do, angle N, angle D. Good. So the lettering actually worked out great. Seems to be kind of coincidental maybe, but it just seems to be working out great for us here. And then again, the whole reason we got the triangles similar in the first place, Audrey, was so that we could get CSSDP, get our lines proportional. So for number 9, we should write by. And there we go. Anyone have this proof exactly right? Basically, except for forgetting to draw the line. Pretty much. Okay, what was the pretty much aspect for you?
I had everything, and then I didn't get the angle 1 equals angle 2. And then...
So you got the right angles equal, but you never got the vertical angles equal, but you still said angle?
Yes.
All right, so just, yeah, make sure we get that in there. That's kind of the point I was making here. I was like, so do we have angle? Well, no, that's one pair of angles. We need one more pair for angle to finish it out. So make sure we get that step in there. Quentin was also kind of ish.
The only thing that I have statement for.
Okay, so you never stated it was a semicircle. You just went to, well, it's in a semicircle without saying it was a semicircle in the first place. Okay.
I did the same thing.
Easy mistake to make. I was proud of Kendall when she said it because I was kind of like, is she going to remember? That's an easy step to skip. So good. Any other questions, comments?
I nailed it.
Don't look now, but I think you guys might be getting the hang of proofs. And at long last, right, for some of you, right? It's like, it's taken a long time, but
This is the first homework I've ever nailed.
It's a process, right? It's getting there slowly, working things through, and teaching you how to put together the logical process. Good job on that. All right, we're going to begin. We've got about 15 minutes left. We're going to begin reviewing for your exam. So I want you to write down some information that you'll need over the weekend to begin studying in earnest for this exam. Obviously, you study a little bit every night. So that way you can do well on quizzes and keep up with things. But maybe a little bit more concentrated study over the weekend. And certainly Monday, you want to spend some time studying as this exam coming up Tuesday. This exam will cover sections 3.8 to 4.9. Sections 3.8 to 4.9. If you're wanting to know where to study in your notebooks, which of course the notebooks also do Tuesday, so over the weekend, making sure those are good to go. In your terms and definitions, you'll begin with tangent. The notes begin for the quarter with tangent. That's where we started the quarter. If you're looking in your theorems corollaries, it would be Theorem 39 is where you would want to start. Theorem 39 and its corollaries, where we would begin. Obviously, the entire properties and transformation section, that's all new. We only added one axiom, like powers, like roots of equals are equal, or like roots of equals are equal. It's duh. So I don't know that necessarily requires a whole lot of study. Constructions, we started this with construction number 9. Okay, so construction 9 is where we began the quarter material for constructions. Quite a bit in class notes, right? Arcs and angles. You have a section there of all the different types of angles and their arcs. That was this quarter. Seems like a long time ago, doesn't it? That was this quarter. Unmemorized constructions, that was this quarter. Now, loci obviously are in your theorems corollary section. It's the memorized loci. The loci was something else we worked on this quarter. So a lot of material to be keeping up with here, but begin studying over the weekend for sure. All right, you can set your books aside for now. Just have out some paper to take some notes on, and I'm going to just do kind of a quick crash course review with you. If you don't know something, write down the term or the fact or something along those lines. Just something to jog your memory so you can go back and study. Don't try to write down everything I say. Obviously, if you know something now, probably going to be just fine when you take the exam on Tuesday. A tangent, it's a line that touches a circle, class at 1 point and only 1 point. But the Clang response to tangent is perpendicular, because a tangent is perpendicular to a radius or diameter at the point of tangency. How many tangents can be drawn at a point on a circle? One and only one, because you can only have one radius to that point, and you can only have one perpendicular to a line, radius, at a point, so only one tangent. How many tangents to a circle from a point outside a circle? Two. And what's going to be true about those two tangents? They will be equal. If I draw two tangents at the ends of a diameter, those tangents will be parallel to each other, because they're both going to be perpendicular to the same line. If I make a polygon that is entirely consisted of tangents, the polygon will be circumscribed about the circle. The circle then is said to be inscribed. Good. We did a construction with that, remember, where we inscribed a circle within a triangle. Well, thereby, the triangle is completely consisted of tangents at that point. We said if we were to have a couple of tangents drawn to a circle, the line joining the 2 points of tangency is called the chord of tangency. Maybe jot that term down real quick. The chord of tangency. Chord of tangency. You go back and look the term up later. Just jot the term down for now. What do we call a line that passes through the centers of two or more circles? Line of centers. What do we call the portion of the line of centers between the centers? Center segment. Good. If two circles intersect each other, what do we call the line that joins the 2 points of intersection?
Line of intersection.
Two circles intersect each other. We join the points of intersection. We have something called the common chord. Common chord. If two circles have the same center, those circles are referred to as being concentric circles. Concentric circles. A line that intersects a circle at 2 points is called a secant. Secant. A region bounded by a chord and an arc is called a region within a circle bounded by a chord and an arc is called a segment of a circle. Obviously, if the arc is a major arc, we have a major segment. If we have a minor arc, we have a minor segment. If we have a semicircular arc, we will also have a semicircle segment. And of course, we already said that an angle inscribed in a semicircle is a right angle. An angle inscribed in a minor segment will be obtuse. And an angle inscribed in a major segment will be acute, because an inscribed angle equals half its arc. If you want to just jot down Theorem 42 and corollaries right there, that's kind of a good summary of those things. Theorem 42 and corollaries. So I'll look from Genesis like, wait! There's your bailout. Theorem 42 and corollaries. That's all that stuff there. So different types of angles. We said again, an angle formed by two chords and the vertex is on the circle. This we would call an inscribed angle. And the inscribed angle equals half its arc. If we were to draw an angle formed by two radii, that's called a central angle. And a central angle is equal to its arc. If we were to draw a couple of chords, but they don't intersect on the circle, they intersect in the circle, this angle would be equal to half the sum of its arc. So it has its own arc, and the vertical angle's arc is half the sum of the arcs. If I were to have an angle formed by a chord and a tangent, An angle formed by a chord and tangent is going to be equal to
Half its arc.
half its arc. If it were to have an angle formed by a secant and a tangent, this angle is going to be equal to half the difference of its two arcs. What about an angle formed by two secants? Half the difference of the two arcs. What about an angle formed by two tangents? Half the difference of the two arcs, right? So two secants, two tangents, a secant and tangent, that's all half the difference. Again, that's Theorems 43 to 45. Theorems 43 to 45. We said if it were to draw on a circle a line intersecting the circle, and it were to draw some parallel line, parallel lines that intersect a circle are going to be equal. Not necessarily.
Equal arc?
Are going to cut off equal arcs in between them. They won't intersect equal arcs, but between them they will cut off equal arcs. So arcs between parallels are equal. All right, then we talked about constructions. Again, look those over the weekend. We're going to practice those on Monday. Your memorized constructions. Of course, we really can't practice unmemorized constructions. I mean, I'm memorized anyway, so whatever I went over with you, you wouldn't see on the test regardless. So know your facts, and you'll be able to figure out the unmemorized constructions. A set of all points, and only those points that satisfy a given condition or satisfy given conditions. Locus of points, or plural would be loci. A locus has two key qualities. First, it includes all points. That means the locus is inclusive, but it only includes points that satisfy a given condition, so a locus is also exclusive. The locus of points, a given distance from a given line would be two lines parallel to the given line, the given distance away on either side. The locus of points, a given distance from a given point. Circle with a given point as center and the given distance as the radius. All points equidistant from the sides of an angle. The angle bisector. All points equidistant from two given points. Perpendicular bisector of this line segment that would join the points. All points equidistant from two parallel lines. Straight line parallel to the given lines, midway between them. Okay. And intersecting lines, equidistant from two intersecting lines.
Or no, two lines drawn in between vertical angles.
You get two lines that bisect the pair of vertical angles. All right, so there's your memorized loci. And we'll practice a few of those compound loci. Let's see, unmemorized constructions.
Can we go over compound loci?
We will on Monday, along as we do the other as well. And then that brings us to our more recent material, which is where the emphasis of the test will be. I've tested you on loci, I've tested you on constructions, I've tested you on arcs and angles and circles and stuff. You haven't had a test yet on ratios, onward. So that's where most of the test is going to be. I'd say about half the test will come from from section 4.1 to 4.8. What is a ratio anyway?
Comparison.
Comparison of two values. A comparison of two values. And again, values meaning it's quantifiable. Like you can't compare red to blue unless you like break it down into like numeric values somehow, right? Like computer, well, even those are so separate you can't even compare that. So yeah, but values, heights, weights, money, lengths, things like that. The first term in a ratio is called the antecedent. Second term is called the consequent. If you multiply or divide the antecedent and consequent by the same value, will you mess up the ratio? No. If you add or subtract the same thing, will it mess up the ratio?
Possibly.
Definitely. Unless it's adding or subtracting 0. So yes, you cannot add or subtract something to both terms of a ratio, but you can multiply or divide by something. If we have two equal ratios, I'm sorry?
Sounds like a sometimes, always, never question.
Doesn't it? Two equal ratios we call a proportion. An equality of two ratios we call a proportion. And What do we call the first and fourth terms of a proportion?
Extremes.
Extremes, and the second and third terms are called the? Of course, we know that in any proportion class, the product of the means equals the product of the extremes. We call this what, Kendall?
Fundamental.
Property of proportions, the fundamental property of proportions. If we have four given values in proportion, the final value is referred to as the fourth proportional. It is possible, though, that both the second and third terms of the proportion could be equal, in which case we would have something called class A, mean proportional, if the means are equal. If that's true, then we have one value in the first spot, another value in both the second and third spots, so now my fourth term is called the third proportional. If we have three terms of one proportion equal to the same exact three terms of another proportion, what must be true? The last terms must be equal to each other. If we have a product of two quantities equal to a product of two other quantities, then either pair of values may be used as the means and the other as the extremes in a proportion. So that if I gave you this statement that 4 times, 6 is equal to 3 times 8. That's a true statement, right? There's a whole lot of proportions we could make. For instance, Quentin, we could say that. Oh. There we go. We can say 4 is to 3 is 8 is to 6. Jamie, we could also say.
What was it? 3 is to 4 as, as 6 is to 8.
Okay, we could say that as well. In fact, there's 8 different things we could form as long as these stay together as either the means or the extremes. Of course, the 3 and 8 would have to stay together as well. The mean proportional can always be found by taking 2 steps. You're going to find the blank of the extremes. Think about it. To find the mean proportional between 2 values, you're going to find the square root of the product of the extremes, right? So if I had 3 is to x as x is to 12, well, obviously we'd have to multiply the 3 and the 12 to get 36. That's going to equal x squared, isn't it? So then we're going to take the square root of the product, which here, of course, would be class positive negative 6. If you were to have a couple of true proportions, say 1 is to 2 is 3 is to 6, and maybe let's pull the 4 is to 3 as 8 is to 6. Given 2 true proportions, you could form a new proportion by taking the products of the corresponding terms. So what proportion would come from these 2? Audrey?
4 is to 6 as 24 is to 36.
Very good. The products of the corresponding terms of a proportion are in proportion. We also said if we had a series of equal ratios, we could form another ratio equal to all of the others. If we said, for instance, 3 is to 4 as 6 is to 8 as 15 is to 20, we could form a new ratio by doing what, Chris?
Adding the antecedents.
Right, so we would get
24 over 32.
Very good. We could add the antecedents and add the consequence, and those sums would have the same ratio. In fact, he didn't even have to add all of them. He could have just added the first couple and gotten 9 to 12. Or maybe these 2 and gotten 18 to 24. Or even the last 2 and gotten 21 to 28. I like that he added all of them for us, though, to get 24 to 32. But a lot of ways you could go with this to form a uniquely new ratio still equal to the others. We had several transformations of proportions. If I were to take these, let's just go with this ratio. If I were to switch these 2 terms, put the 8 here, the 3 here, class, that's called?
The inverse? No.
Alternation. Alternation. If I were to add the 4 and 3 to get 7, 8 and 6 to get 14, but then keep the 4 and the 8, that would be the addition transformation. If I were to flip them both and get 4 over 3 and 8 over 6, that would be inversion. If I were to take the 4 and 6 and trade and the 3 and 8 and trade, that would be alternation. If I were to switch both means and extremes places with each other. If I were to subtract, of course, and then keep one of the original, that would be Subtraction transformation. If I were to square everything, that would be a power transformation. And that brings us up to pictures and proportions, which we'll review on Monday. There is no homework other than make sure your notebooks are ready to go for Tuesday. Make sure you spend some time studying in preparation for the exam on Tuesday, and you are dismissed.